Just 1 minute, please.
Okay.
Some slide there.
Okay, thank you.
Welcome back. We want to continue with our lessons in our mathematics lessons and try to implement again in Rust. So yesterday we looked at how to convert number systems, and today we want to look at modular arithmetic. It's something we already have an idea of what to do. So we just, the main thing is how do we implement this in Rust? Modular arithmetic has several applications in computer science. And some of the applications are construction of the pseudo-random numbers, hashing functions, and cryptology. And so you discover that this is a very important topic. And so therefore we need to know to go about with it in terms of implementation of in Rust. Now, so I begin by this definition: let m be a positive integer. So when do we say that these two numbers a and b are congruent? When do we say that these two numbers are congruent? Mod m. When do we say that a is congruent to b? Or when do we say that b is congruent to a? Mod m. So that is the question here. And the answer as is here, we say that a and b are congruent, mod m, if m can divide their difference. If m can divide the difference of these two, then we say that those two numbers are congruent, mod m. And therefore, we write it this way. And that is how we read it. We read a is congruent to b mod m. That's how it's read. A is congruent to b mod m. We've already said what that means, that if a is congruent to b mod m, then it means that m would divide the difference between a and b. Now, if m cannot divide that difference, this is how we write it. M cannot divide the difference of a minus b. If that is the case, then we say that a is not congruent to b mod m. That's how we read this statement. A is not congruent to b mod m. Now, so I just want to show examples of just to emphasize that definition. Example 21. The question is 10 congruent to 4 mod 3? So for us to answer this question, we subtract 4 from 10 and divide the result by 3 and see if that is possible. So when you subtract these two, you get 6. Does 3 divide 6? Yes, it does, because the remainder will be 0. So we say that a number divides another one if the remainder is 0. What about the next example? Is 10 congruent to 1 mod 3? So that means, again, we subtract 1 from 10 and divide the result by 3. So this would be 9. And it's true that 3 divides 9. So 10 is congruent to 1 mod 3. What about this other one? I've said that 15 is not congruent to negative 5. Let's see if that is true. We just take 15, and then from it subtract negative 5. What you get here is 15 plus 5. 15 plus 5, because minus and minus will be positive. That is 20. And it's true that 15, it's true that 3 cannot divide 20. 3 cannot divide 20 because there will be a remainder. And the last example here, we take 22, subtract 4 from it, we get 18. And then does 5 divide 18? The answer is no. 5 does not divide 18. Therefore, it's true that 22 is not congruent to 4 mod 5. Now, so how do we get numbers which are congruent to another one? That is what I want to look at. How do we get a number that is congruent to another? Numbers that are congruent to 3, for example, when I'm looking at this example. Which numbers are congruent to 3 mod 7? So we're asking which numbers, when you subtract 3 from them, the result that you get will be divided by 7. That is the question. So which numbers? You see, it cannot be only one number. There are several numbers, which when you subtract 3 from them, the result will be divisible by 7. So what are those numbers? So to get those numbers, we have to understand what this means. What this means is that, just before that, there's something to guide us here. Something to guide us. They have said, given these 3 numbers, if m is greater than 0, we can also say that b is congruent to a mod m if b can be written in terms of a and m. If b can be written in, so that is why you say that b is congruent. For instance, when we say that is to find a number that is congruent to 3, so that number should be written as a number that is congruent to 3 should be written in this form. Should be written in this form. So let me call this number b. Let me call this number b. So b should be the same as a. A in this case is 3 plus m. M is our mod 7. And then t. T is any integer. T is any integer. This z means integer. T is any integer. That means t can be 0, t can be 1, t can be 2, t can be -1, t can be -2, and so on. So if you take t to be 0, for instance, if you take t to be 0, then you find that b will be 3. If you take t to be 1, then it is here. If you take it to be 1, you'll be talking of 7 plus 3, which is 10. If we take it to be 2, then this will be 14 plus 3, which is 17. So all these numbers, there are so many numbers which are congruent to 3. So for instance, you can see that this 10 is congruent to 3 mod 7. You can see that because when I subtract this from this, the answer that I get is 7, and 7 can divide that 7. You can also see that this 17 is congruent to 3 mod 7. Because when I subtract this 3 from 17, I get 14, and 14 is divisible by 7. So there are so many ways. So that is where we want to begin with writing our code. And let me just explain how we'll be writing that code so that it becomes easier for us to write the code. A code that will give us numbers that are congruent to another number. I'll just again repeat what I've just explained, and that is how we'll be writing the code. Now, so we want numbers We want a number A which is congruent to 3 mod 7. That's what we want. So want to, from this reasoning, want to see how to come up with a code. So for us to find this number, we said that this A should be written in the form 3 plus 7t. Now, if you write it this way, where in this case, t is 0, 1, all the way up to where you want it. Suppose you want it to go to 10. Suppose you want to go to 11. Supposing you want 11 digits. Suppose you want, okay, this is if you want 10 digits. If you want, no, 12 digits. If you want 12 of them. So 0, when it is 0, you get a value. You get that A. You get that A. If t is 0, let me just use my values here. If t is 0, you get 3. You get 3. The value here, positive value. You get 3. When t is 1, this is 1 times 7, which is 7 plus r is 10. Get the next number. When t is 2, this will be 14 plus that gives 17. When t is 3, this will be 21. This will be 21 plus that gives 24, and so on. I have the negative values. If I want the negative values, I change this sign. I change that sign to negative. So I would have A can also be given by 3 minus 7t. And this time, since I want the negative values, t will range from 1 to up to where you want it. It will range from 1 to up to where you want it. For instance, when t is 1, this value becomes 7, negative 7. And when you add it to 3, negative 7 plus 3 is negative 4. And that is the value I have here. When t is 2, this becomes negative 14. Negative 14 plus 3 will be negative 11. When t is 3, so the thing is, if I want the positive values, what will be, how do I define my t? If I want positive values, my t is defined to begin from 0 onwards. If I want the negative values, and I change the sign here first, I change the sign, and my t now ranges from 1 onwards, not from negative 0, not from 0. Because when you put 0 here, you have a 3 which you already have. You have a 3 which you already have here. You have a 3 which, if you put a 0, so we begin from 1 to get the other values, the negative values. Now, so that is how I write the code, and my code is here. The code is here. Just look at it. Just give me 1 minute. See, look at it. Okay. I can now explain this code. The main function, I want 9 values. I want 9 values. 9 positive values and 9 negative values. That's what I want. As I've said, this specifies the positive and the negative numbers that you want generated. So I want 9 values. So I will then say let count be 9. Let count be 9. So that means I want to have 9 positive values and 9 negative values. Now, let positive numbers. So this is now to generate, this is what will generate the positive numbers. So I say, generate positive congruent numbers 3 mod 7 and then count. So what does this 3 mean? These 3, the first one here, the first 3 is the number we want, the number that is, we want numbers that are congruent to. The number that we want, numbers which are congruent to. And this is the mod. And the count is what we've defined here. 9, in this case, positive values. 9. Then let negative numbers. So this one is to now define the negative numbers. Generate negative numbers or negative congruent numbers. So we want numbers which are negative and are congruent to 3, mod 7, and they should be 9, again, the count. Then it will print 2 results. The first result will be the positive numbers congruent to 3 mod 7 are. So it lists them here. Then it prints negative numbers congruent to 3 mod 7 are. It lists those negative values here. Now, so this is what generates the positive values. I've used I62, I use 32. I also use I128 or I64. And also the mod, you can, if you want a bigger mod, you can change these I's. And I'm using I because I want negative and positive values. So that is why I have I. And of course, I'm using I also because my 3 here could be negative 3. I may want values which are congruent to negative 3. So that is why I use I. Of course, you can use U if you don't want. Look, the range I talked about, if you want the positive values, the range is from 0 to the count, 0 ... to the count. So the count is 9. So 0 to count. And then the formula that we've been talking about is here. That is the formula I was giving. So in this case, our congruent is 3. And then mod is 7. There's a K. So K 7. In our case, we said it was, in above example, it was 70. So K is just the number, and K is ranging from 0 to the count. K is ranging from 0 to so this is the formula. The formula. And the formula is saying the congruent, now the number that is congruent, which is 3, plus K, and K is an I32. I32, you can use I64 and so on, times modulus. Then it will collect those numbers as a vector. Collect them as a vector. Then this will again be giving us, this function will be generating the negative values. And it's the same thing. It's the same thing up to here. It's the same thing. And the range I've already talked about, the range is beginning from 1 to the count. 1 to the count. And then the formula again, I talked about this formula. In this case, it's 3 minus k times modulus. Our modulus is 7. Then it will collect again the values as a vector. Now let's try to, let me just see if we can open it and try to run. Can you see it?
Yes.
I've told it that I want 11 positive values and 11 negative values. So you can see I've added here the notes that this is just to specify what you want. I want to generate values which are congruent to 17 mod 32. 17 numbers which are congruent to 17 mod 32. So it will give me the positive values. It will count 11 of them. Then again, this other one, let the negative values. So again, I want which are congruent to 17 mod 32. Let it count and give me 11 values. Then it will print that result. The formula is here. The formula I was talking about has been defined here. To give me the positive values, the range is from 0. And this other one, the range is from 1. And so to give me the negative values, let us run this. Now, when you run that, you can see the positive values, numbers congruent to 17 mod 32 have been listed here. How many are they? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then the negative values that are congruent to 17 mod 32 have also been listed here, and are also 11. Now let's try the question that we just did. The question that we did was, let's get 15 values. Let's get 15 values, and we were doing 3 wanted values that are congruent to 3 mod 7. Want 15 of them, which are congruent to 3 mod 7. So it will be giving us 15 negative values and then 15 positive values. Let us again run this. Yes, it has done that. Let's see if there are 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And also the negative values, there are 15. Let's now increase the numbers. Let's increase the numbers. I want to have which number? Let me just write the number there. If it let's also have the mod. Mod, you can even have 713. It's no problem. I just want to make this one 713. If it refuses, we move further to 64, I64, then move to I128 and see whether we can get the result. Let's see if it will do this. What does it say? Let's read what it says here. It's out of range. Out of range. You can see that error. Can you see the error at the bottom?
Yes.
Yes, it says it's out of range. That means I32 will not work. And let's try to increase to, in fact, it has said something here, consider using type I64 instead. That's what it's saying. In fact, sometimes you get the advice from this, it gives the error and then it advises you what you could try doing. Let's try what it has just said. Just at this point that we want to change to I64. Then also change here. If it refuses, we move further. We want the number that is given also to be I64. And then this formula, I64. And then let's come here again, the same thing, 64. But this is how the code is written. And then again here, I64, let's try to run it now. Yeah, it has given us values. It has given us values. It says the positive numbers congruent to 17 mod 32. What is that? Where is 17 mod 32 coming from? It reduced this number to let me see. Oh, we didn't change here. We didn't change here. So 17, it's from what we asked it to print. It only to print that way. So we just changed that part. I was wondering where the 17 32 was coming from. It's here. Where the result, where we told it to, how we told it to say the result, how to print the result. So you can just change this. Yes, if you change that, it will give you this, the correct thing. Yes, positive numbers congruent to this number, mod 713, and we asked for 15 of them. There are here 15 of them. And the negative numbers, we asked for 15 of them. Again, they'll be here. They'll be here, all of them. They'll be negative numbers. So the negative is not here, but you just include the negative. The numbers here are negative numbers. So that's how we write the code for numbers which are congruent to another number. Now, I already explained the code. So these are the notes. You just go through it. The main function sets the count, how many positive numbers you want and how many negative numbers you want generated. Then it generates the numbers. And then the positive ones will be stored as in positive numbers and the negative will be stored as negative numbers. Then there's this part which generates the positive numbers. I've already explained about, the only thing we need to know here is the range and then the formula. The range and then the formula. And then of course, we know I32, we know what it means. So I've said generates a vector of positive congruent to congruent modulars. So it will, for instance, in this case, it was 7. It will generate numbers which are positive and are congruent to congruent. Congruent here was 3. A congruent to 3 modulars, which is 7. Then the range the range, the count, up to the count, but the count minus 1. Count minus 1. So that means if you want 11 values, you said count was 11. Count was 11, but it begins from 0 to 10. So if you count 0 to 10, those are 11 values. Those are 11 values. And then the formula is here. The formula is here. Then the next one, to generate the negative numbers, is the same thing. The formula just changes here. Instead of positive, we have negative. At that point, the formula changes. And again, the count from 1 to the count. So if you wanted 11 numbers, it will do from 1 to 11. K will range from 1 to 11 if you want 11 numbers. But for the positive, if you wanted 11 numbers, K will range from 0 to 10. And this will be 11 numbers, and again, this will be 11 numbers. I've emphasized that formula here. Okay. Unless somebody has a question there, I want to go to something related to that. And I'm defining, if I'm given an integer a and m, where m is greater than 0, m mod m. What is m mod m? So we already had talked about this. So when we talk of m mod m, we are talking about what remains when you divide a by m. What remains? That's how you understand this. What remains when you divide a by m is what we call m mod m. So 14 mod 5. We're asking ourselves, what is the remainder on dividing 14 by 5? And earlier on, we had talked about that. So when we talk about the remainder, this thing, you write it as 14, 5. This means the remainder, when you're writing the Rust code, the remainder on dividing 14 by 5 is 4. The remainder will be 4 when the remainder here. So this means the remainder. Now, so the remainder of 139 on division by 10, that remainder is 9. The remainder of this on division by 5 would be 1. In fact, how you do this, using the code. If you use the code, Rust code, it can give this an answer as negative 14. But for you to ensure that you have the positive value, you take the negative 14 and add 5. You get negative what? You get negative 9. Again, add 5. Get negative 4. Again, add 5 until you get a positive value, and the positive value will be 1. So you tell Rust you want a positive value. And so to tell it, want a positive value, then this is how we will be doing it. Now, what about this? Again, you're dividing by 5, and the remainder is 3. And this is the same reasoning as here. The same reasoning as the one I've already explained. We are adding 9 to that, and 9 again, until you get a positive value. For the first time, if you just add, you get 5, because this is a smaller number. Now, the Rust code that will do this question 1, the Rust code that will do that question 1, can do this question B. It can do this question D. It can do this question F, because you just change something, just adding. It's just addition. Can do this question G. If you modify it the way I've talked here, If you modify the way I've talked here, and then it can also do question C, and then it do question E. And then from there, we look at a different code to do question H and I. Let me just go through the rest code that it does A to G. It's a very short code. It's a very short code. I've said use I64 to handle large integers. Otherwise, you would still delete I. If I delete this I64 and this, so that I just have, if I just leave it this way, if I say let A be 14, let B be 5, it will assume that I'm using I32. It will assume that I'm using I32. So then I decided to be specific that at this time, I want even to handle bigger values. I want to handle bigger values than I32. Now, compute the remainder. This is what I've written here. Compute the remainder on dividing A by B. That's what it means. So this is what you write. Let the result, we see the question here is, the question is this, 14, what is 14 mod 5? What is 14 mod 5? This is the question, and I've just called 14A and called 5B. Now, what is my result? My result will be the remainder on dividing A by B. I've added some notes so that I had said that if 14 is negative, that is what I have here. If A is negative, you can modify this part. Because why we modify? We modify it to be this way. Modify it. Let me just erase this modification. I'll say the modification is you add the modulus. So the remainder, you see, Rust will, if I have negative 14 mod 5, Rust will give me this, what I have here, what I have up to here, what I have up to here. This result would be negative 14. That result would be negative 14. So for me to ensure, and in fact, most negative 14 is correct, but I want this value to be positive. So for me to have it positive, I would say the remainder plus B. That's the way I was explaining. So for instance, in this case, the remainder plus 5, and I will add that 5 until I have positive value. So just take the remainder plus B. Then the answer you get, again, find the remainder on division by B. If you find that the answer again is negative, add B. You add B again, and so on and so on. It will print the result. And I've said this code can also handle A plus C mod B. Let me just try to open it. This one is, let me find out where it is. Okay, so I have it. Where is it? Here. It's a very short thing. What is making it long are just the additional notes to assist in understanding what we are doing. Now, so I want 7 mod 5. In other words, I want the remainder on dividing 7 by 5. Kagoran. The remainder is 2. I just need to change this part. This part, just change that part, then we run again. Yes, it says the remainder of 7 divided by 2. You can see where I'm highlighting. Yeah? Can you see the part I'm highlighting at the bottom?
Yes.
Yes, it says the remainder of 7 on dividing by 5 is 2. Good. Let me try 17 and change this part also to be 17. That will again be 2. Let me try 18. 18. Let me try 18. Try 18, which is supposed to be 3. On division by 5. Run. Yes, it says when you divide 18 by 5, the remainder will be 3. Let's try 18 plus 40. Just say plus 40, 18 plus 40, and then divide by 5. This is, can just write, in fact, that is just 58. Just 58. Go run. Says the remainder will be 3. Let me change the divisor, 7. Let's see. 7 here also. Change 7 to 7. So I said this one can deal with addition, and just if you want to add, it still can still work. So it gives me that the remainder will be 2. Of course, that is 58, and 7 were to go there, or it will go there 6 times. Huh? No, go there 8 times. Yes, 8 times because of 56. The remainder will be 2. Now let's come back to the negative number. A is negative this time, and I was saying that if this code up to here will give us the result to be negative 4. Let's see. Yes, it says. Let me just change this. This part is supposed to be negative 4. Negative 4. That part. Change it. It says negative 4. The remainder on dividing 7 into negative 4 is negative 4. Of course, we know that it's supposed to be 3, positive value. So to get it positive 3, that's what I said, that we just modify this part. Modify this part. Let's modify this part. The remainder of A on dividing by B, then we say we add the mod to it, and then close the bracket. You can see it's red, meaning that there is a problem. So let's close that bracket. And then now, the result that we get, again, get the remainder on dividing by B. On dividing by B. So let's try again. Let's try now. Yeah, it gives us a positive value now. Now it gives us a positive value, which is 3. In fact, we can leave it that way because even if this number is positive, it will still give us the same, a correct value. If I write 15, it will still give us a correct value. In fact, we can leave it that way so that it can deal with both the negative and positive values. Instead of having two different codes, we can just leave it that way so that becomes the correct code. Again, let me run. Now let's now increase these numbers. Let's increase these numbers. Okay, let's run. It says the remainder is this. I've never changed this part. This one is a bit easy. Just change this part to have the correct the correct thing here. But it's saying if that number divides the number above, the remainder will be this. The remainder will be that. Okay, let us see about if we say plus that. Let us run. Again, it has given us a result. The only thing you need to change is this part, which is here. Just change that part. Good. That is how we do that question. So what remains is just what about if we are multiplying? Let's go back there. I just want to show the code and then we end the class. If we are multiplying a raised to n times b raised to t mod m, the question is, what is the remainder when you divide this result by m? That is a question. What is the remainder when you multiply this, divide the result by m? So for you to do that, a very small code just from here up to here. Let the result, I just went to the result straight away. My internet is a bit unstable. Let the result, this is the number, this is our A, M. I've said let it be I32 power. So our N, this case I'm using N to be 2. Then times our B is 13. And I'm saying let it be an I32. Of course, you can have an I64, an I128. Power. And my power T here I've taken to be 2. Then my M I've taken to be 14. It will print the result. It will print the result. Let's look at the code. So that is if you want to multiply, that's how you do it. Here it is. You can see it, eh?
Yes, we can.
So I want 11 raised to 2 times 13 raised to 2 mod 4. So I just begin from here. Let result 14, now 11 power 2 times 13 power 2 on division by 4, what is the remainder? Okay, let me run this. Says the remainder is 1. Says the remainder is 1. You can let's change this. Let's change this to 17. And change this to 19. And we want to divide by 7. Want to divide by 7. What will be the remainder? The remainder is still 1. What about if we divide by 9? What about if we divide by 9? What will be the remainder? The remainder is still 1. Okay? Let us increase this power to 3. Let us increase that power to 3. Okay, very good thing here. When you go to 3, what does it say? Oh, no. I not type. I typed something. It's supposed to be cargo around, so it wrote something different. Yeah, the answer is 8. The remainder is 8. So I increased this power. Let's go. Okay, if you just want times 9, that means the power is 1 in both cases. The power is 1. Just change that power to 1. If you want 17 times 19, the answer you get divided by 9, and you want to find out what the remainder is. So just change the power. It's just the power that you change. And again, the answer is just still 8 for this case. What about if we divide it by 7? Will the answer be 1? The answer is 1. The answer is 1. I want us to go outside I32. That's to go outside I32. Let us run. Says it cannot. Says the thread panicked at the attempt to multiply. There was an overflow. That means it went beyond what we were looking for. It went beyond I32. Let's see whether changing to 64 would give us a result. Sometimes it will not. And if it does not, then we modify our code so that we can have it run. I've changed it to I64, yes. Everywhere, yes. It doesn't run. What about if I change it to 128? 128 is the highest we can go. So the highest we can go. That is the highest we can go. Oh, it has given us some result. It's saying it is 0. The remainder is 0. That means this, what we get here is divisible by 7. Okay. What about if I increase it? Want to go beyond so that we can modify it to something new. I want this power to be 7. And this power to be 7. Let's see. Yeah, there's an overflow. There's an overflow. So that means it will not work for this one. But if we reduce the values, it will work. If we reduce the values, it will work. Now, so what happens in that case? What happens in that case, let me just explain as we used to do it in the class. If you have a number, just explaining, then we go to the code and we end the class. If you have a number like, let me say 900, let me write it here, 9999 raised to 2 mod 7. This is what we used to do. What you see, the code that we have is this. It has 999, then raised to 2, then mod 7. And this number here is becoming too huge. Too huge. So what we used to do in our class, we first of all used to reduce this number. First of all. Then the number that we reduce, we now raise it to 2. For instance, when we had 5 raised to 4 mod, let me say 36, mod 5. What we used to do in our class, because we discovered this number was becoming huge, so we used first of all to reduce this number, mod 5. So we divide 5 here and find the remainder, and the remainder is 1. Then we take 1 raised to 4, mod 5. So this is how we are supposed to modify this code so that it can now do this question that we've just tried and it was not working. So first of all, reduce this mod 5. Find the remainder of 36 on division by 5. The answer that you get, raise it to 4. And then after raising it to 4, again, find the remainder on division by 5. So this is how we're supposed to do it so that it runs. Otherwise, it will not. Otherwise, it will not. Those numbers can be very huge. Can be very huge. And so the modified code that then does that is the one that I'm showing here. It's the last code for today. It's the one I'm showing here. I discovered that there'll be big numbers, and so therefore I have this library and this library for power to assist us do powers. And these ones for big integers. And then now the first number, I'm doing the first number first of all. Reduce it. I reduce it mod 5. So the number is 19, for instance. My power is 4 exponential. The exponent, not exponent, the exponent. That is a power. So the base, my first base, base 1. Let base 1 be this big integer. And I'm using 19. And then let the first exponent 1 before, mod 5. Mod 5. And then this is what I'm multiplying with. The second base, I'm using 288. Using 288, the second base. And the second exponent 2, I'm using 8. And then the big, the modulus, mod 2. Of course, mod 1 and mod 2 are the same. So this the whole thing, mod 5. Now, how do we calculate? How we calculate? The calculation is, first of all, it does this thing, mod 5. Then does this thing, mod 5, then combines the two results. So you can see, let result 1 be base 1 raised to this power, the first exponent, base 1 raised to the first exponent, mod the first modulus. Of course, the first modulus and the second modulus are the same. There are cases where you can want them to be different. There are cases where you may want them to be different. And so again, it will still work. Now it will do for this part. And then this part is doing for the second part. The second result 2. You take base 2, which has been defined, raised to power exponent 2, which has been defined as 8, and then find the remainder on division by modulus 2, which also has been defined as 5. Okay, after you've done that, then multiply the 2 results that you get. So that the final result, therefore, the final result is result 1 times result 2. There is a possibility that this 2 might also be bigger than our mod. And so again, we divide by the mod and get the remainder. We divide by the mod and get the remainder. And so you have the result. Let's just look at the code. Let's look at the code, just looking at it, and then we end at that. Let's just look at the code. Just let me open it first. Okay, here it is. Let me look at the cargo TML. I have defined dependencies. Since I'm dealing with big integers, I've defined these dependencies here. They are supposed to be there. Let's go back to the main code. And this is what we have, the library. Libraries there. And then this is for the first integer, the base, the power, and the mod of the first integer. Again, for the second integer, we have here the mod, the exponent, and the base, the exponent, and the mod. And then we come to do the result for the first integer. The result for the first integer, then the result for the second integer. Then we come and combine the 2 results. And I'm saying that this we shall just use mod 1 because mod 1 and mod 2 are the same. So let us just run this and see what we get. So this will work with even bigger numbers. The one that 128 was unable. Now the result is 1. It has given us a result of 1. Of course, you can also change U32 to U64, even here, and so on. So that's how you do. This is how the code, you make the Rust code for these questions. Thank you. Unless somebody has a question, I'll stop there.